Hello, I'm Bob Friday, and thanks for joining us on another episode of Bob Friday Talks. I am joined today by former professor of structural biology at Leiden University and now director of data science here at Juniper Networks, Navraj Pannu. Today we're going to be discussing his journey from professorship to network data scientist. Welcome, Navraj. Maybe we can start our conversation today a little bit about how did you, what got you into being a professor?
I think what got me into being a professor, but also the transition from structural biology to networking, is my love of mathematics. That's a common link. I love applied mathematics. I love solving problems with mathematics, testing out the problems by writing software, and then validating it.
Okay. Now structural biology, exactly what does that mean? So you were working on...
So what we were trying to do was developing algorithms to solve the three-dimensional atomic coordinates of protein or DNA molecules. So why is that important? Essentially, they are the building blocks of life. With that knowledge of the three-dimensional structure, we can understand how the protein functions and the basis for diseases. So many diseases are caused by mutations in that protein. With that structure, we can correlate to the function and then develop drugs to combat disease.
Okay, so I've read a couple of your papers, and it sounds like, before joining us, you were working on solving the problem of immortality, aging. I almost regret hiring you, So tell me exactly how the proteins aging all relate to each other.
So at the fundamental level, aging or cancer is caused by damage in DNA, or can be caused through damage in DNA. Our body has a whole system of DNA repair proteins that repair damaged DNA all the time so that these mutations aren't propagated to have malfunctioning proteins. And as we get older, or if we're exposed to radiation, for example, sun, the DNA damages more, and hence we have these problems. So one of the aspects I was working on in the Netherlands was, in collaboration with experts, trying to determine these DNA repair proteins and understanding the mechanism of action.
Okay, so I've got to ask you now. So you're working on networking, trying to solve networking problems and building solutions on par with domain experts. How close were you to solving this aging problem?
Oh, I think I was more into solving the particular DNA repair pathways associated with certain diseases. The aging problem is still ongoing, trying to understand how we can reverse aging. It's an active area of research at the moment, but with more knowledge that we have on all the different pathways and how our DNA can become damaged, the more we'll get to solving this problem.
Okay, I don't want to feel too bad about hiring you. It's like, solving aging, that's a pretty critical problem to be solved. Now, I understand also that, when you're working on this problem, really AI wasn't around at the time. Maybe describe a little bit to the audience, what techniques, I know you were visiting linear accelerators and stuff, whatever, when the hell did you need to go to linear accelerator for?
So we employed statistical methods in order to solve the structures of proteins. So what we had to do first was collect the experimental data. So we first grew crystals of the protein of interest, and then we would take it to, for example, synchrotrons. At that synchrotrons, we had access to highly intense X-ray beams. With that, we could collect a diffraction pattern. That diffraction pattern gave us the information we needed to solve the three-dimensional structure of proteins. And through statistical methods, we are then able to determine the atomic coordinates and analyze the molecules.
Okay, so you were building a big simulator. You were trying to build simulation to simulate how all these proteins and amino acids were folding. Was that the basic technique?
So indeed, we developed a model in order to determine the atomic coordinates, but it was based on the experimental data. But then, as I moved to the Bay Area, a transition occurred, and that was actually using AI methods. So based on the hundreds of thousands of protein structures solved, DeepMind and Google got involved to try to solve try to solve structures without the need to go to the synchrotron to collect the experimental data. So they trained a model to try to predict the fold of a protein molecule, and they were very successful at doing that.
Okay, so this is the transition when you decided to transition from academic to back into industry and data science. Maybe a little bit more about that transition, and is this a case where AI actually put you out of business? How many years were you working on this protein problem?
I had started as an undergraduate in 1996, developing algorithms and applying them to protein structures. I was very interested in AI, yet I realized in order to do it and understand AI methods, coming to the Bay Area would be the best solution for me. So indeed, it was a huge transition going from academic to an industrial environment. But at the end, it was all about the mathematics. And another advantage, coming to the Bay Area, you have access to a tremendous amount of data. With that data, for example, what we have at Juniper Mist, we can tackle big problems and model the situation.
Okay, so the team at Google DeepMind actually were able to solve this problem with some sort of deep learning AI technique and eliminate the need for the simulators and the models.
Yes.
Can you give the audience a little bit about, how much do you know about DeepMind and what type of models were they using to, solve this protein problem? Similar to what we see with ChatGPT, or are these different type of models?
The models are not transformer based, but they are deep learning. So in the case of GPT, we have billions of data parameters. For the case of DeepMind and their deep learning model, they have access to maybe 100,000, but they probably truncated their training data to a bit less. But there's a great deal of information within each of those structures. And they were able to develop a target function that understood the protein folding problem and then validate the model since they had access to all this data. So this was a revolution because previously, as you mentioned, most people were just they considered it a big optimization problem. They weren't looking at the vast amount of data available, and they were just thinking, oh, if I optimize this problem and I search all through parameter space, maybe I could get to the answer. They ignored all the data that my colleagues, my fellow structural biologists had, and that was a difference that DeepMind.
Okay, so now you're at Juniper Mist. You're working on trying to build a solution that can manage, operate networks on par with human domain experts. 1 minute you're trying to solve aging, proteins, and now we're overall trying to build something on par with human IT domain experts. Similarities, proteins, networking.
I think the key similarity is just the scientific approach. You have to define a problem. You have to know the data that you have and the limitations. So in the case of Juniper Mist, we had access to both Zoom and Teams data. This gave us an indication of the quality of the data. But thanks to your efforts in part, we had all this data in the cloud that we can combine with that data. So we can determine which network parameters or client parameters are affecting Zoom calls. So we have developed a model to do this, an AI-based model. And because we have access to millions of data, we're able to then train a very accurate model and then, more importantly, validate that model.
I make a barrel of wine, and what I've learned is that organic chemistry is a hell of a lot harder than wireless. Trying to make a good bottle of wine, wireless is much easier. What do you think? Solving the protein problem, solving the networking problem, same level, easier or harder?
That's a great question, by the way. The best approach is just to iteratively improve those methods. So at the start of the protein folding problem, people, as you mentioned, were just trying to simulate the model, right? They weren't using the vast amount of data, but then they learned to use all the data. There's still some networking problems that exist that we'll tackle in the future. We started off with getting this labeled data from Zoom and Teams. We had a well-defined problem. We had a huge data set. and then we could try to explain the issues. Now, the powerful thing, we have all of this expertise at Juniper Mist, and they could validate that problem as we validated whether we came up with the correct solution or not. And that's, I think, the key. We have the end-to-end process all the way up to validation. So I realize I might not have answered your problem completely, like what is more difficult, but this I think is a big first step to having AI methods in networking, including like the post-connection problem, which we can then create even more problems and general problems.
And maybe on the journey, give the audience a little bit, in terms of building a model that can accurately predict Zoom and Teams, where are you on the journey? Can you actually accurately predict a Zoom Teams user experience now, or are we still working on that?
We are able to accurately predict a Zoom client minute. So, for example, what do I mean by that? If a client were to have a Zoom call, we can predict, for example, the latency or the packet loss that client is experiencing or will experience. How do I know that? Based on the metrics, based on our validation training data set. But so what? So what's the big deal about predicting latency and packet loss? The nice thing that comes along with AI is this whole idea of explainability. Once we have an accurate model, which we know from our statistics, we can try to explain that. And that is what our customers really like. They like looking at the feature ranking. So what are the important network parameters? So for example, is it a capacity issue? Is it a coverage issue? Or is it a client issue? That's what our customers want. And that's what we're providing them. And we validated it not only internally, but externally as well.
Now I've heard you talk about Shapley, maybe for the data scientists in our audience here, maybe give a little bit of explanation, mutual information, Shapley. How does this Shapley help you explain the network features responsible for the prediction?
So at the core of Shapley is I have this concept that I've mentioned a few times, and let me define it. I call it a feature. That's what's used in AI. What this is essentially a network parameter we are using to try to predict the model behavior. So some example of features that we're using are the client's RSSI, or the number of clients on the AP, or the return trip time from a particular AP. So Shapley considers every single combination of all of those features in order to explain which one is dominant. And that's what we want to know. Which feature is dominant that's leading to this poor network performance? And the mathematically proven fact is that Shapley values are objective and unbiased. So we know that it can provide this information. So in contrast, mutual information, it only looks at pairwise comparisons. So you can only compare for example, the latency from Zoom with that particular feature. Okay. You can't compare at a multivariate level.
Okay, so it sounds like we have a model, we have Shapley. Maybe give the audience a little bit. How much data did it take to train this model? Are we talking like terabyte? Is this like ChatGPT where you took the whole internet and trained this model on?
So at the moment, what goes into training a model is usually 1 million data points. So what I mean by a data point is that we have the labeled latency that we're getting from either Zoom or Teams. And then we are combining that data with all of our Juniper Mist network data. So combining that all, we train the model, and we use that model to then predict what our clients are experiencing.
Maybe for the audience, an example of how this is really helping customers, or the needle in the haystack problem that IT teams face?
So we've uncovered a few issues, but one of the things that we've seen that has been quite prevalent is the idea of a customer connected to a VPN server. So before, both Zoom and Microsoft Teams have identified that a VPN server can be deleterious to a call. But something that we have discovered is that it's actually not just the VPN server that is an issue, but actually the distance from the client to the VPN server. And if there is a large distance, say someone connecting from India connecting to Australia, that leads to a very poor video or audio performance.
Okay, Navraj. Well, I have to say I'm starting to feel a little bad, solving the aging problem, solving the network problem. Still not sure I made the right decision, but maybe for other young professors and data science coming out, any words of wisdom and advice on their venture into the data science AI world?
For me, at least from my experience, as I started off with, I love mathematics. I found the area that I really enjoyed doing, and I found the place that I've always been lucky that I found a place where I can do this and apply it to problems which I think are very critical to me. So that's the number one thing. If you have that passion, you will be able to find something that you enjoy doing, whether it's structural biology, where there's still a lot of room for improvements, whether it's networking, or even natural language processing, developing something like GPT. There's so many areas of AI. So I love, for example, thinking about ethical AI, thinking about the hallucination problems of GPT. How can we get around that? I mean, these are all open areas, and there will always be room and always be, just keep in mind, I think the guiding principles are the scientific method of experimentation, testing, and validation, and then reiterating.
Well, Navraj, I want to thank you. It's been a pleasure working with you, I can say. And I want to thank everyone for joining us today on Bob Friday Talks, and look forward to seeing you on the next episode.